This video is about the Rayleigh-Ritz theorem, which involves a quantity called the Rayleigh quotient. So we assume we have a symmetric matrix. The Rayleigh quotient is just defined as this quantity where you have your A matrix and you multiply it from the left and right with x transpose x, and then you divide it by x transpose x. So it's a symmetric matrix. We can order the eigenvalues and these will be the eigenvector. The Rayleigh-Ritz theorem is a characterization of the eigenvalues. So, for example, lambda 1 can be obtained by minimizing the Rayleigh quotient such that x is any vector in Rn. So if you take the minimum of the Rayleigh quotient over all vectors, you will get lambda 1. In fact, the Rayleigh-Ritz theorem is a family of statements, and lambda 2 can be obtained by again minimizing the Rayleigh quotient vector, but we also assume this, which is an orthogonality condition. So we assume that the x that we minimize here, so the set of vectors that we minimize over is restricted. So it's a subset of Rn, and it's the subset of vectors that are orthogonal to the first eigenvector. So to get lambda 2, you minimize over all vectors x that are orthogonal to the first eigenvector. And similarly, so to get lambda 3, you need to minimize the Rayleigh quotient. You take the set of all vectors, but you restrict it. You restrict it by keeping it only vectors that are orthogonal to the first eigenvector and the second eigenvector. So the subset of vectors in Rn that are orthogonal to both the first and the second eigenvector. And then you continue, and the lambda n is obtained from n-1 orthogonality conditions. Let's do an example. First, we note that we can assume this. So assume without loss of generality that the x vector is normalized. And this is due to the fact that R of x is independent of the scaling of the vector. We can see this directly by just inserting alpha x as a vector in the Rayleigh quotient like this. Let's look at this matrix here, which has eigenvalues -1 and 3. So we now need to parameterize, so look at all vectors that are normalized. And all 2 by 2 vectors that are normalized, they are given, you can parameterize them using the trigonometric functions. So we have here, this is a parameterization of all vectors that are normalized. And let's look at how the Rayleigh quotient looks for different values of alpha. We see here that this is the Rayleigh quotient as a function of theta, and the smallest eigenvalue was -1, and we see here that this value here is the minimum. We have observed here exactly what's the statement of the Rayleigh-Ritz theorem, that the minimum of the Rayleigh quotient is exactly equal to lambda 1. Here's another example where we take a 3 by 3 matrix and its eigenvalues are -2, 1, and 5. You could obtain -2 by taking the Rayleigh-Ritz theorem for lambda 1. Now we're going to compute lambda 2. And we note here that the first eigenvector is v1. Now we want to look at the vectors in R3 that are orthogonal to v1. And because of this vector is the third unit vector, we can parameterize all vectors that are orthogonal to v1 using, again, trigonometric functions. So this corresponds to all vectors that are normalized and orthogonal to v1. The corresponding plot looks like this, and we see here that we have 1 here, and the minimum is again obtained here is 1, which is exactly this value here. So we have verified the Rayleigh-Ritz theorem for the second eigenvalue.